Now we can approach the same problem in a manner that's more consistent with the way we've developed the equations and the reasoning process and so forth, by just interpreting deceleration in a way that allows us to write out what delta TA and VF are. So let's assume that V naught is positive. Okay, so the ball comes into the mitt, that's in the positive direction. This is the positive direction. Well, since you have a deceleration, the acceleration's in the opposite direction. That's what it takes to decelerate something, to slow something down. Okay, so it turns out that A is going to have to be negative. Now we could have assumed that V naught was negative, and then A would be positive. The result that we get for V naught is going to depend on whether A is negative or positive. Okay, well, in this case A is negative because we want V naught to be positive. Delta T is 1.85 times 10 to the negative third seconds. No need for absolute value signs or any kind of gyrations involved with the idea of deceleration. The acceleration, as we said, is negative, so that's going to be negative 2.10 times 10 to the fourth meters per second. There's nothing inherent in this problem that makes the acceleration negative. The only thing that makes the acceleration negative is that we declared at the beginning that V naught was positive. Had we wanted acceleration to be positive, we could have declared at the beginning that V naught is negative. Okay, well, this is all consistent with our definition, and obviously the ball comes to rest, so the final velocity is 0. So, now I'll note that we could use the second equation of motion here. Vf equals V naught plus A delta T. Very easy to solve that for V naught. But if we do this, we're going to get the same thing we get by reasoning, so I'm going to reason it out. And unless otherwise specified, you're free to make your choice as to how to do it. Acceleration then is delta V over delta T, and this comes from the definition. Acceleration is the average rate of change, the average acceleration is the average rate of change of velocity with respect to clock time. Now we're in a uniform acceleration situation, so we can drop the word average since the acceleration is always the same. Okay, well, so we get acceleration is delta V over delta T from the definition, starting with the words. Okay, so we have delta V over delta T, and that's what? Delta V is Vf minus V naught, so that's Vf minus V naught over delta T. Note that A equals Vf minus V naught over delta T is exactly what you would get if you solved this equation for A. Okay, we're not going to solve the equation for A because A is a known quantity. But this reasoning is identical in every respect to the equation, identical in every respect except the way the quantities are arranged algebraically in the equation. Okay, well anyhow, there's your acceleration. Now we know that Vf is 0, so 0 minus V naught is just negative V naught, so the acceleration is negative V naught over delta T in this particular case where Vf is 0. Now, if we just take acceleration equals negative V naught over delta T and solve for V naught, well, first we multiply both sides by delta T. We get negative V naught equals A delta T. And then we multiply by negative 1. We get V naught equals negative A delta T. And we can plug in our acceleration and our delta T. We have negative of the negative 2.10 times 10 to the fourth meters per second multiplied by our 1.85 times 10 to the negative third seconds, our 1.85 milliseconds. And again, we get about 36 meters per second. Now, we could have solved this equation for V naught, and we would have gotten the same expression since Vf is 0. We would get, without going through the solution, solving for V naught, we'd subtract A delta T from both sides, and actually that would be it. So we get V naught equals Vf minus A delta T. In this case, that's going to be 0 minus your negative 2.10 times 10 to the fourth meters per second squared multiplied by your 1.85 times 10 to the negative third seconds, and this calculation is identical to to this calculation. So had we used the equations of motion, we would have come out with very similar expressions and identical results. Now we're asked to calculate the net force on the ball by the mitt if the mass of the ball is 0.5 kilograms. Now we know that the average net force is mass times the average acceleration, and I guess I should put net down here. Okay, so the average net force is mass times the average acceleration. In this case, then, the average acceleration is the acceleration, negative 2.10 times 10 to the fourth meters per second squared, and oh my goodness, I've been really careless with my units here. There's a second squared here, and there's a second squared down here. Let me get the right color chalk. And I think I've written it out correctly everywhere else, like over here. I just got careless when I reworked the problem. And you can excuse me or not, but that's what I did. Okay. And don't do that. Okay. Don't do what I did. So we end up then multiplying the 0.5 kilograms by the negative 2.10 times 10 to the fourth meters per second squared. And this second also has to be squared. We get negative 1.05 from multiplying half of 2.10 is 1.05, 10 to the fourth, and it's going to have units of kilograms times meters per second squared, and a kilogram times a meter per second squared is a newton, so we have negative 10,500 newtons, which is, of course, 1.05 times 10 to the fourth is 1.05 times 10,000, which is 10,500 newtons in this case.